Okay, welcome back everyone. So today, I'm making another video on LaTeX, and today, basically, also don't mind this. This is just a quick sketch. I called it PNG dog because why not? Today is just going to be just a fairly short video, hopefully, and I'm just going to be coding, or I don't know if you can really call this coding. I'm just going to be writing down a problem on this LaTeX workbook, just solving it here, and I already did. Two problems in the past, so here they are. And actually, I haven't finished this one here, so we're going to get this one done as well, hopefully. And I have the problem prepared here. Kind of wrote it out quickly, so it's not very nice. And Sketchpad to if we need to ever do any work, which we probably will need to do. So there we go. We have everything ready, and I'm not going to be talking much here. It's mostly just going to be coding, and yeah, let's just get started. Okay. So let's just finish up this problem. I'll just tell you where I'm at with this problem. Basically, the problem was that a rock on some planet is dropped. Oh wait, I just run this because I think I didn't run something. Oh, what did I do? Okay. Okay, yeah, there we go. So problem A, and then problem B will be my next thingamajig. Okay. So here's the problem before this, and here's the problem that we still need to finish. So it's problem 1.4. A rock on some planet is dropped from 20 feet. It takes 2 seconds for it to hit the ground. How long would it take if it was instead dropped from 200 feet? What is the speed when it hits the ground? We're assuming the acceleration is constant. Okay, so here's my solution, and I got pretty far into it. So just me reiterating, this is the method I'm going to be using, just like it's called the toolbox method, if you will. And basically you write out what you know, and you do whatever you can with that info. So here we go. Basically just some basic integration. We assumed our acceleration was constant, so you take the integral of that, and with respect to time, take it our velocity function, yada yada yada. And here we just use the fact that our initial velocity is 0. So essentially v of 0 is just 0. And we use that there, and we got that our C1 is 0. Same process here. We took the integral of that to get our position function, and we got our initial position to be 20. So we already know that that's C2 now. And here's our function, our position function. This will be useful. Okay. And we will also get that. We also got that at time equals 2. Basically, our height will be 0, right? That's when it hits the ground. So we can use that. We use that, and I got that k will be that k is 0. Sorry, that k is minus 10. And there's something wrong, I think, actually, because I was trying to use begin and end align, but it didn't seem to work. That usually works. That's really weird, actually. Let's see. Huh. It should definitely be working. Let me just quickly check something. Begin align. See, I used it here, basically the same way. What's the problem then? Kind of confused. That's really weird. Let's see. Yeah. What the? Hold on, I can't quite tell what's going on. Okay. I'll just Okay, so I'll just like retype this out. Usually I don't get issues like this. Flash begin align, and then type this out. This should work, right? So if we run this, nope. That is pretty annoying, actually. Huh. It's basically the same process. I don't know what the problem is. Is there... Oh, I see what I've done. Okay, there we go. Just need to do this. That's the problem. I see. There we go. So that's what we wanted, right? So we have basically the reason for the align was that I wanted the process of simplifying this to be aligned, and finally to get our k value of k. Actually, it would be nice if I flip this around, maybe. So just k equals minus 10. Yeah, that's good. Okay, so minus 10 feet per second squared. That's our constant velocity on this planet, which is not Earth, of course. So now what we need to do is, well, let's check it out. So we want to. The question asks us how long would it take if it was instead dropped from 200 feet? Well, let's see. If we can basically what we can do here is we can. Did it say how long? Let me check. Hopefully. Yeah. So we can just take our position function. Okay. Let's take our position function. First, take our function. First, take a look, I suppose, at the position function. Okay, and then we can just use our begin green. Then I'm gonna try not to talk that much. Okay. Beginning green. Just making the formatting look nice, as nice as I can. Okay. Now, okay. Okay, I think I misinterpreted it actually. So 200. Okay, I'll just keep it there for now. Since we want to try finding how long it will take for the okay. So basically, our new position function would be, let's check it out. So how long would it take? I just want to actually get rid of this here. And then this is fine, right? Get rid of this. See how that looks. I'm probably not gonna like the look of that. I guess we can have like a paragraph here. Separate paragraph. Yeah, I get that weird thing there. Let's check it out here. Okay, I'm just not gonna worry about that then. Okay, that's fine for now. Since we want to find out how long it would take if the rock was thrown from 200 feet, only our initial position will change in this case. Okay, so we just have okay, let's just 10, okay, Control X, equation simple enough. Okay, and 1/2. So our initial position, our initial position will just be 200 instead of 20. Right. And since, yeah, okay, so it should be 200. And basically we want to find out when, okay, we want to find out when it's 200. So, well, how long it would take if the rock was thrown from 200 feet. Okay? So, how do we reason through this? So at what time, basically, is now, since our new initial position is 200, now we want to find what our time is when basically height is 0. Okay? So that's the plan. Okay. Okay. So we can actually do slash align, I suppose. We can align abstract. That's all I want. Align. Okay. And then same process. Yeah. So this is equal to 0, right? Then we want to subtract minus sign from both sides. Then we'll get a positive value. We'll end up with a positive 200. Okay, good. So our good sign is that our time will actually be positive, and that's a good thing because we can't have negative time, right? At least in our universe. So we just have 200 equals slash frac 1, 2, 10 times t squared. So then just basically divide by 10, we get 200. Okay, so that's fine with me. Looks, oh yeah, we still have a 1/2 there. We have to remember that. I don't know, I actually don't know why we never simplified it. Our position function. Let me see what this looks like actually. Yeah, I don't know why we left the 1/2 there. We could have just set this to 5, right? We don't need the frac there anymore. So we should just have -5 t squared plus 200. Nice. Okay. So again, okay. Nice. And just get, okay. Yeah, that's a good sign. Okay. Yep. So now, I'm just looking through my work so I don't make any careless mistakes. Yeah. Okay. Just remember to do this. Yep. Okay, divide by 5 and take the square root. Square root. So the square root, basically we'll get the square root of 40. No, we'll do it step by step, okay? 40 and equals t squared, and then finally we just get square root. Well, we still have, I think we'll have one more after this. Equals t, and then we can simplify this by just taking out the 4, so we just have 2 times square root 5. Right, simple enough. Uh-oh, sorry, it's 10. I can't really simplify further. And there we go. So, oh, I see what I've done. Yep. I didn't add the aligning thing, whatever you want to call it here. I'm kind of tired, so don't mind my voice. So, in our classic tradition, we can just flip these around. That's what we've been doing. Great. Okay, so that's our time. That's our new time. So that's, we can just do like some. I wonder if frame box works here. I hope it does. I don't think it does actually. I've tried it before, and then I just get like so many errors. So maybe that's because I don't have this. That could be. I don't think so. Yeah. So it's probably because I'm just in align mode. Yeah. So there we go. And just to make it clear, this text it, this leaves us with an answer of 2 squared 10 for the first part of our problem. Okay, it's taking longer than I thought actually. I don't know why it's taking so long. So next part, what is its speed when it hits the ground? Okay, well that's pretty simple, right? It's basically, so what is its speed when, so what is the velocity? Okay, so what is the velocity when time is equal to, well, however long it takes us normally? I think this just applies to the normal scenario, right? So to do this, we can just, Actually, let me see about this. Okay, so we know our k is minus 10. And again, what this is asking us is equivalently saying that what is its speed? Okay, so it says what is its speed when it hits the ground. So what is its speed? So we can use our velocity function. And when it hits the ground, okay. When it hits the ground. Okay. So we just want to set our original position function to 0. Right? And then we just get 4 times square root of 5, I think, for our time when it hits the ground. Oh, sorry, no, that's the wrong one. I need to look at this one. So original would be 20, and we just get 2 at t is equal to 2. Oh wait, normally it's very interesting actually. I think my intuition is correct, right? I mean, I think I got this right. I really don't know if it's asking for this, for that case, or this case. Or, okay, what is its speed when it hits the ground? I'm not sure what it means. So, 3 seconds. It's pretty aggravating. Let me see something real quick. Okay, well I think I split this into 2 parts. So I'll see you in the next video. Goodbye.